Good afternoon, everyone. Welcome to the EFG webinar, The Formation and Chemical Evolution of the Moon as the key to assess its potential metal resources. My name is Magnus Johansson, and I'm the Secretary General of the European Federation of Geologists. I'll be the host of this webinar. The European Federation of Geologists is organizing these webinars periodically to foster the professional development of geologists, as well as to increase the public awareness on the importance of geoscience. Today, I'm very happy to present the speaker of today, Renaud Merle. Renaud Merle is a researcher at the Department of Earth Sciences at the Uppsala University of Sweden. He's been working there since 2020. He graduated with a PhD in geochemistry at Nantes University in France in 2006. As a postdoc, he's been working in several different institutions in Europe, University of Geneva, the CRPG in Nancy, France, the Swedish Museum of Natural History, and as well as the Curtin University in Australia. He has studied the chemistry of terrestrial lavas for 18 years using isotope geochemistry and geochronology. Since 2012, he's been working on extraterrestrial lavas and materials using samples from the US Apollo and Soviet era lunar missions, meteorites from the Moon, Mars, and the asteroid belt. And currently, Renaud is developing a new research theme regarding chemical element resources of the Moon. Before I give the floor to the speaker of today, I want to remind you that after the presentation, there will be a question and answer session. And we invite you all to propose questions to the presenter in the YouTube chat. We will select and answer some of these questions at the end of the webinar. And without further delay, Renaud, please, you can start when you're ready.
Thank you, Magnus. Thank you, everyone, for attending this webinar. And as Magnus said, it's about the formation, chemical evolution of the Moon, and how it is important to understand the nature of the potential resources of the Moon. What are those resources, where we can find them? But before that, I thought that maybe to put things in a context was necessary, because we have all in mind the term space mining. And we have in mind movies and books, sci-fi movies and books about space mining. And I can show you 3 examples here. And they are talking about mining titanium or large-scale mining operations, and of course, drilling asteroids. But I don't think that's sci-fi anymore, because the NASA is really serious about it. That's the headlines of The Guardian at the end of 2020, and NASA is looking for private companies to mine the Moon. So yeah, it's not really sci-fi anymore. But then we have to ask, why using the resources of the Moon? And of course, why going back to the Moon? And there's 2 questions are clearly connected together tightly. And that's probably the difference between the space race we witnessed in the 60s. And nowadays we are witnessing another space race. We have a renewed interest in solar system exploration since the last, say, 10 years. Some say it's because of the competition with China. China has landed the first object on the moon in 2013. That was the first object to land on the moon since 1976. But I prefer to think that, well, the solar system is the last frontier, like polar exploration in the early 20th century. The main questions are, why going back to the moon? Why using the resources of the moon? And there is a practical interest in solar system exploration because the moon is our closest neighbor. If we look at the distances of the other objects in the solar system, the closest, excepting the moon, is Venus, 105 million kilometers away. That's huge. The moon is only 360,000 kilometers away. So we are talking about space missions that will last about a decade. And if we think about the moon as a launching pad where we have bases, we solve a lot of problems because we don't have to bother about the takeoff and re-entry of the spacecrafts that are risky operations. We can also build spacecrafts that will be more fuel efficient. For the moment, we have big rockets with huge fuel tanks for a ridiculously small payload, but we will not have that if we have a base on the moon. And we can consider this because we have potential resources available on the moon, especially if we implement the concept of in situ resources utilization. That means harvesting the resource we can find on the spot. And again, NASA is really serious about it. And again, this is an article from The Guardian, and NASA indicated that they want to harvest resources on the moon to prepare exploration of the solar system, in particular Mars. And this is the core of the Artemis program, utilization of resources from the moon. And in this case, the moon will be the gateway of the solar system. But even before looking at what the resources are, we have to think about how they formed. Because on the moon, we have no fluids, we have no atmosphere, we have no ocean, we have no erosion, no plate tectonics, no recent or active magmatism. That means no regional scale metamorphism, no metasomatism. All these processes are leading to the formation of resources on Earth, but they do not apply here on the moon. That means that all the resources of the moon must be related to its initial formation and rocks that formed during the early history of the moon. So let's look at the geology of the moon, I should say the sinology, and you can more or less work it out by looking at this very familiar image. You have the black spots, and that is basalt, more or less like the rocks erupting from the Hawaiian volcanoes or in Iceland. And the bright patches, this is the crust. It's the anorthosite crust because it's formed by 90 to 100% anorthite, a calcium aluminium plagioclase. And covering everything, we have the regolith. That's the lunar soil. It's formed by the meteoritic impact since 4,500 million years. And it's a mixing between basalt, anorthosite, and impact bridges that were formed by the successive impacts. And the regolith covers all the planet. But how do we have this information? Well, we have the landings, Apollo and Luna and the Chinese missions. We have also meteorites. We have also remote sensing data. But in terms of rocks, we have just less than 600 kilograms of rocks. But with this material, we were able to draw an history of the early evolution of the moon and how it formed. So let's have a look at it. And everything started with a very chaotic process about 4,500 to 4,400 million years. We don't really know about that. But what we suspect is a giant impact between a Mars-sized object and Earth. The consequence of this is that all the volatile elements are gone. By volatile elements, I mean sodium, lead, arsenic, nitrogen, oxygen. And what remained are the refractory elements, calcium, titanium, aluminium. We have good evidence about that because we have similar oxygen and titanium isotope ratios for Earth and the Moon. Then, following this initial impact, we have what we call the planetary differentiation. That happened between 4,500 and 4,400 million years. Again, we don't really know. But what happened, we had an accumulation of heat from the initial impact, and we have the heat from the radioactive elements. And that led to the formation of a global magma ocean, an ocean of magma covering the entire planet. And we call it LMO for lunar magma ocean. And as soon as this LMO formed, it began to crystallize. And what happened is that the first minerals to form were iron and magnesium rich, olivine, then pyroxene, and they sunk into the liquid because they were denser and they formed different layers. So we have formation of a stratified mantle with layers of different compositions. But then at some point, we have formation of plagioclase, anorthite. But because it's less dense than the remaining liquid, it floated, forming a compact crystal network that will eventually form the anorthositic crust. But this is a model. It's not confirmed so far. Then, once we have a mantle, we can melt it to produce a volcanic activity. Again, we don't really know when it started, probably around 4,400 million years. And apparently, it lasted until 2,000 million years. As soon as we got basalts from the moon, we began to analyze them. And we sorted them according to their chemistry, basically according to the titanium content of these basalts. The main group, the most abundant, is the low titanium basalt group. They have a titanium content which is lower than 6%, and it is subdivided in different groups, but for this talk, I will just mention the low uranium-238 lead-204 ratio basalts. We call them the low mu, and they are depleted in rare earth elements and other mineral incompatible elements compared to the other basalts. We believe that the source of these low mu basalts is a depleted source. Then we have the minor group of the high titanium basalts. They have a titanium content which is higher than 6%. And both the low titanium basalts and the high titanium basalts are apparently derived from the different layers formed during the LMO crystallization. And in addition to these groups, we have the weird basalts. We call them creep because they are enriched in phosphorus, potassium, rare earth elements, and uranium. Compared to the other basalts, they are enriched in rare earth elements and other incompatible elements, and we believe they are derived from an enriched source. In fact, this source is probably the last liquid formed during the LMO crystallization. And this source would be sandwiched between the crust and the mantle layers source of the low titanium basalts and high titanium basalts. So with this early history of the moon, we can guess what could be the resources of the moon. Again, we don't have much data, but there are a few things we know. And let's start with the regolith. Most of the elements present in the regolith are originated from the crust or the basalts or the breccias formed by the different and successive impacts. So we expect to find lithophile elements like silicon, magnesium, calcium, and manganese, titanium and rare earth elements, of course. I have to mention two resources that are not originated from the moon: oxygen coming from Earth and helium-3, which could be used in fusion reaction as a fusion reaction fuel. There is another interesting aspect about the regolith in terms of natural resource, that is its property to shield against heat and radiation. So we could use the regolith as a concrete. We call it lunacrete. But the most interesting potential resources on the moon should come from basalt and crust. If we look at the anorthosite crust, 95% calcium plagioclase, we expect to find aluminium, silicon, calcium, and strontium. And if we compare the lunar crust with the crust of Earth, and this is what you see in this diagram, the lunar crust here in blue contains more aluminium and more calcium than the crust of Earth or even the lunar basalts. The lunar basalts, they are formed by iron magnesium silicates, olivine, pyroxene, also plagioclase, iron titanium oxide, phosphates, and sometimes native metals. For some of them, the iron content is up to 14%. So we expect also to find a lot of magnesium, cobalt, nickel, titanium. And again, if we look at this plot, clearly the lunar basalts contain more titanium than the crust of Earth or even the anorthosite crust, more magnesium, more iron. But let's look at a few chemical elements in basalts and anorthosite. Let's start with aluminium. The main ore on Earth is bauxite, a mixture of aluminium hydroxide and iron oxide and hydroxide. The metallurgical grade is between 42 and 44 percent. But if we look at the anorthosite from the Apollo 16 landing site, we have some rocks with an aluminium content up to 35%. So that's not really far from what we can find on Earth. For titanium, the main titanium ore on Earth is ilmenite, and the largest titanium mine in Europe, in Norway, has a grade of 18% of titanium. Again, if we look at the some high titanium basalts from the Apollo 17 landing site, we have a titanium content which is up to 15%. Again, we are not far from what we can find on Earth. Another example, rare earth elements. So in this diagram, basically you have the rare earth elements sorted according to their atomic number. And here on the y-axis, you have the normalized concentration, normalized to the average composition of carbonaceous chondrites, which is probably close to the composition of the initial solar system. So we have a few classic terrestrial rocks like the mid-ocean ridge basalts here in black. We have the average composition of the crust of Earth. We have basalts from hotspots like Hawaii here. And we have also carbonatites, Alnö carbonatites in Sweden, Bear Lodge carbonatite in US. And we have also the Norasjö nepheline cyanide, also located in Sweden. Why carbonatites and nepheline cyanide? Because from these rocks we extract rare earth elements. The blue field here is the field of the lunar basalts. And here in red, you have the crypt basalts. And what you see is that for the middle rare earth elements, but in particular for the heavy rare earth elements, the lunar basalts have higher concentrations than most of the terrestrial rocks, including carbonatites. Okay, no match for the Norasjö nepheline cyanide, but still, in particular, the crypt basalts, particularly enriched in heavy rare earth elements, which are used for laser applications. Let's see at the distribution on the planet of resources. And let's take the example of thorium. And this is an image made by remote sensing, and you have the thorium concentration. And here you have this huge anomaly. We have a thorium content between 5 and 12 ppm. By comparison, the crust of Earth is 4 to 6 ppm. But if you look in more details at this anomaly, we can see that it's closely associated with basalts. In fact, this area is named the Procellarum terrain. In fact, we name it Procellarum crypt terrain because many of the basalts we recovered from this area tend to have a creep component in their chemical characteristics. So we have a lot of questions, in fact, when we have seen all of this. What are the processes involved in the formation and location of resources? We have seen that the distribution and content of many resources are tightly connected to the basalts. That means if we want to better understand what can be those resources, where they are located, we need to understand the origin of the chemical characteristics of the basalts. That means we need to identify what are the sources of the mantle sources of the basalts and how those mantle sources formed. And we might be able to answer few questions like why creep basalts are so rare, why these basalts are enriched compared to the other basalts. Should we expect other chemical types of basalts with high contents of chemical valuable elements? So how we investigate lunar volcanism? Well, we can go into the geochemist's toolbox and use radiogenic isotope geochemistry. The principle is the radioactive decay of a parent element into a daughter element. So we have the radioactive decay equation. We measure the number of atoms of the daughter element, which is the result of the amount of this isotope initially present and the decay of the parent element. For practical purpose, we normalize this equation with a non-radiogenic isotope of the daughter element, and we have this equation in which we have two very important parameters: the initial ratio of the daughter element, and that traces the chemical characteristics of the sources, the mantle sources of the basalts, and we have time of formation of a rock. So the methodological approach: first, we determine accurate and reliable chronology for the lunar basaltic magmatism, and we determine initial ratios of radiogenic isotopes in lunar basalts. How we do date lunar basaltic rocks: we have classic radiometric techniques, and usually we use what we call the isochrone. So you recognize the same equation again, and how it works: basically we have a plot where we have different rock forming minerals with different parent-daughter ratios, in this case rubidium strontium, but because they form from the same magma, they have the same initial ratio, the same initial strontium ratio here. But then we have radioactive decay of rubidium, so the rubidium strontium of the different minerals evolves, changed, and eventually they form a line, which is the isochrone, and at the intercept of the y-axis we have the initial isotopic ratio for strontium that trace the sources of the basalts. So you might think, oh, since 50 years we should know better about the lunar magmatism, the sources of the basalts. No, we don't, because in fact we have limited constraints on the chemical characteristics of the mantle sources of the basalts. We have in fact, very few radiogenic isotope data. Most of these data have a large uncertainty, so they are not significant. And in fact, we don't have isotope systematics using strontium, neodymium, lead, hafnium initial isotopic ratios, something like these diagrams, something that you would see for terrestrial basalts forming trends towards mantle end members. And that is stemmed to another problem. Again, you see this classic equation. That's the initial ratio for old magmatism, like on the moon. We measure this ratio. We have to correct it for the decay of the parent element. So we need time to obtain the initial ratio. But we have poor chronological constraints on the timing of the volcanic activity. Again, despite 50 years of lunar studies, we have few data. They have low precision. Sometimes we have an inconsistency of dates obtained by different techniques on the same sample. We have methodological and analytical issues. So we need better dates, and we have also to filter the existing data. So the working group to which I belong, mostly located at the Swedish Museum of Natural History, has developed a new technique since six years, more or less, 7 years, that is in situ lead dating by secondary ion mass spectrometry, or SIMS. The principle is also based on an isochron, but we have a 7,6 lead versus 4,6 lead isochron. And this isochron is made from in situ analysis of minerals containing lead. The advantages of this technique: we analyze only lead isotopes. We have a high lateral resolution, and we can monitor terrestrial lead contamination. I explain this to you immediately. So let's start with the lead isochron. It's a bit different from the isochron I've shown you. Here on the x-axis, we have the 4,6 lead ratio, and here we have the 7,6 lead ratio. All the minerals that formed at the same time in a crystallizing magma form a line, an isochron, but the intersect of the y-axis gives the composition of radiogenic lead. And using this formula, we can calculate the age of the rock. The initial lead composition is located here at the top of the isochron. Now the lateral resolution, that's the possibility of analyzing small individual grains containing lead. This is what you see in this image. You have the scale bar 500 microns, and you see there's tiny grains. They are probably 10 microns, no more. And usually we target phosphates, potassium feldspars, zirconium oxides, and zirconium silicates. Then we need to monitor terrestrial lead contamination. By experience, we know that uranium lead data contaminated by terrestrial lead tend to yield older dates. As I said previously, lead is a volatile element. During the initial impact, it was removed from the moon. So the moon has very low lead concentrations. That means if we contaminate lunar samples with terrestrial lead, the contamination is very strong, even with minute amount of terrestrial lead. In practice, when we plot data in a 4676 lead diagram, we don't have an isochron usually, we have a triangle. It's a 3-component mixing between initial lead, terrestrial contamination, and radiogenic lead. But we have established a statistical procedure to remove these data points step by step until we reach the leftmost line of the triangle here. We call it the leftmost isochron. And doing this, we are now quite confident that we can calculate an age that is not biased by terrestrial contamination. So we have dated since the last 7 years, probably 30 basalts, I think. I also looked at the previously published data, not only uranium lead or lead, but also from different dating techniques. And this is what I've got. So we have all the basaltic rocks, meteorites, Apollo landings, lunar landings as well. And what we see is 2 main magmatic phases. The oldest between 4000 and 3600 million years, and the youngest between 3400 and 3100 million years. So now we have a better idea about the chronology of the volcanic events on the moon. So we can go back to the radiogenic isotope ratios, and we can start with lead. And again, you have a 4676 diagram, but in this case, we have the isotopic composition of basalt plotted in this diagram. And this is an early model, and what we tried to do is to match the composition of the basalts with model curves and modeling the evolution of the lead isotopic composition. And of course, we had to make assumptions for this model. So we start with the age of formation of the moon, which we are not really sure about. And we have this evolution curve, which represents the LMO. Of course, we need the uranium-238 lead-204 ratio, mu. And then we need the age of the differentiation of the mantle sources of the basalts from the LMO. Again, we don't know this age. So, and also we assume in this model that the sources of the basalts formed at the same time. So we decided to change that and remove the assumptions. What we did is to start with the composition of the low mu basalts and the creep basalts, because we thought that they were representing 2 extreme compositions in terms of mantle sources. And what we did is to try to estimate the mu ratio of the source of the low mu basalts and the creep basalts. To do that, we took a set of values corresponding to the age of formation of the moon, the age of the differentiation of the mantle sources of the basalts. We also took a set of values for the mu of the LMO, and we ran Monte Carlo simulations. And what we saw is in fact convergence of the values towards a single value for the low mu source, 90, and for the creep basalts, the source of the creep basalts, about 3,600. But then we can look at the other basalts. They are basically plotting between these two evolution curves. And what we see is trends, in particular for the low mu basalts. And if we plot the lead isotopic composition of the low titanium basalts versus age, we see that the oldest basalts tend to have a stronger, say, low titanium affinity. In fact, less weakest creep involvement, while the oldest basalts, the youngest basalts here, tend to have a stronger creep component in their chemical characteristics. And we interpreted this plot as a mixing. So we tested it. Again, you have this classic plot where you have the evolution curves of the low mu basalts and the creep basalts. And here, connecting those two evolution curves, you have mixing lines here. And they correspond to a mixing process at a given time. On these lines, we have the data points of basalts, and the age of the basalts correspond to the age of the mixing event modeled by these lines. So it works for lead, but it works also for strontium and neodymium. So we can explain the composition of the low titanium basalts as a mixing between two components, 10 to 20% creep component, 90 to 80% low mu source. But then how we can explain this in terms of a geodynamic process? What is the driving process? What we think is a thermomechanical erosion of the creep source layer. Remember, the layer sandwiched between the crust and the other mantle layers. But to do that, it means that we have some kind of convection. So, concluding remarks for now, we still don't know a lot about the nature, occurrence, and distribution of the natural resources of the moon. But we can see with the rocks we have, we can see there are potential metal resources. Titanium associated with high titanium basalts, rare earth elements associated with creep basalts. But of course, the nature and distribution of resources are highly dependent of our understanding of lunar mantle formation and evolution. Convection explains the chemical characteristics of the low titanium basalts. That means we should expect more creep contribution, a stronger creep signature in the basalts that are younger. We still don't know, or we don't have strong constraints about the origin of the chemical characteristics of the high titanium basalts. And again, the bottom line is that our current knowledge is based on a very limited number of sample and data. So let's go back to the moon. Thank you.
Thank you, Renaud, for a very interesting presentation. We'll have some minutes for answering the questions. and we invite you to submit through the YouTube chat. The first questions have already appeared here, and we have a question on the cause of the radioactivity in the initial remelt process, so to say. What caused this, or which isotope is responsible for that? Do you know anything about the cause of this melting in the model proposed?
Well, we are at the very first stage of the solar system formation. We are talking about less than, I would say, 50 million years after the formation of the sun. So we have a lot of radioactive elements. So we have uranium, 238, 235. We have also potassium. Potassium is probably the most abundant. And like on Earth, the huge amount of potassium is probably responsible for a lot of heat. And with the heat from the initial impact, well, that is possible to melt the rocks at the planetary scale. We have also other radioactive elements that are now extinct. So yeah, a lot of different radioactive elements, but I bet potassium is probably the most important because very abundant.
Thank you. A question about the platinum group. We talked about, you mentioned titanium, that there are REEs, potentially interesting, aluminium, but are there platinum group metals? Do you know anything about that?
Actually, no. I expect them to be actually in the core of the moon because these elements tend to be siderophile. But actually, I don't know. I don't know. They are also refractory at some point, some of them. So we should expect them to be more concentrated on the moon. But I have to admit, I didn't look at them. I would say if we want to recover PGEs, I would mine the regolith because the moon is constantly bombarded by meteorites, and meteorites from the asteroid belt tend to be quite rich in platinum group elements.
Thank you. Another question concerning the depletion of volatile elements generally seen. Is there any evidence for magmatic differentiation of the basalts to enrich these elements locally, or even hydrothermal processes?
Hydrothermal processes, I don't think so. Again, we don't have fluids on the moon. I would say the volatile elements were depleted during the initial impact, the giant impact. Then we have studies that documented magmatic degassing. So I don't think the volatiles are very enriched in lunar basalts. And for example, I would be tempted to say that the crypt basalts are the most depleted in volatile, but again, I'm not sure.
A question about the use of resources and the economic feasibility of using resources and the time frame potential for using.
Well, for sure, for the moment, it's not economically feasible, considering the cost of space missions. But in the time frame, for example, for the Artemis mission, the NASA is talking about the mid-2030s to establish some kind of base. So, and it will not be an economically viable operation. I would say it will be a small scale operation. Again, using the resources we find on the spot to build something to develop solar system exploration. We are talking probably about a time frame of, I would say, 50 years. I don't expect that we will bring stuff from Earth, from the moon to Earth in the next immediate future.
Considering the processes of the formation, there's one question about the Sudbury Basin-like or meteorite impact-related deposits. Is there any potential for similar on the moon?
That's a long-lasting debate among the community of lunar scientists. People believe there are evidences of formation of melt lenses after very big impacts, but that is debated. Again, I think Sudbury, we have involvement of fluids, which is not the case on the moon, excepting magmas. So it's difficult to answer.
We need to go there and research more, definitely.
Absolutely.
About the formation, is there any other model? I mean, what I've heard is corresponding with this gigantic Mars-size meteorite impact with the Earth, creating the moon. But are there any other model or hypothetic formation procedure?
Yes, you have models that are slightly different from this one. But you have also very different models, like, for example, the moon formed by accretion from dust and material from the proto-planetary disk, the disk of material that remained after the formation of the sun. That doesn't work because, if I remember correctly, the core of the moon is about 20% of its volume. While if you compare with Earth, the core of Earth is 50% of the volume. So there is something different about the moon. So this model doesn't work. And again, so far, we have strong evidences from isotopic system, oxygen, but also titanium isotopic systems. They are similar, the isotopic ratios are similar for Earth and the moon. So there is a genetic link apparently between the moon and Earth. You have also an interesting model is that you have accumulation of radioactive elements on Earth. And because of the rotation of Earth, they accumulated in one specific area and they formed a natural reactor. And then you had a chain reaction and you had basically a nuclear explosion. And that ejected material in space from Earth, and that material formed the moon. I kind of like this one.
Yeah, like space fireworks, so to say.
Somehow, yes.
Yeah. Well, I think we've reached the end of the webinar time, and I thank the audience for the questions. And Renaud, many thanks for presenting in this webinar.
Thank you for inviting me.
So it was great to have the audience and you, as well as the crew behind the stage supporting us. Take care and see you in the upcoming webinars. Thank you.
Bye.